In mathematical logic and computer science, the mu-recursive functions are a class of partial functions from natural numbers to natural numbers that are computable in an intuitive sense. In fact, in computability theory it is shown that the mu-recursive functions are precisely the functions that can be computed by Turing machines. The mu-recursive functions are closely related to primitive recursive functions, and their inductive definition builds upon that of the primitive recursive functions. However, not every mu-recursive function is a primitive recursive function. The most famous example is the Ackermann function. Other equivalent classes of functions are the lambda recursive functions and the functions that can be computed by Markov algorithms. The set of all recursive functions is known as R in computational complexity theory. Definition: the mu-recursive functions are partial functions that take finite tuples of natural numbers and return a single natural number. They are the smallest class of partial functions that includes the initial functions and is closed under composition, primitive recursion, and the mu operator. The smallest class of functions including the initial functions enclosed under composition and primitive recursion is the class of primitive recursive functions. While all primitive recursive functions are total, this is not true of partial recursive functions. For example, the minimization of the successor function is undefined. The primitive recursive functions are a subset of the total recursive functions, which are a subset of the partial recursive functions. For example, the Ackermann function can be proven to be total recursive, but not primitive, initial or basic functions. p. 219. For more about some of the various symbolisms found in the literature, see Symbolism below. Constant function. For each natural number and every alternative definitions use compositions of the successor function and use a zero function that always returns 0 in place of the constant function. Successor function S. Projection function. For all natural numbers such that operators. Composition operator. Given an mary function and mkary functions. Primitive recursion operator. Given the kary function and k plus 2ary function. Minimization operator. Given a ary total function. Intuitively, minimization seeks, beginning the search from 0 and proceeding upwards, the smallest argument that causes the function to return 0. If there is no such argument, the search never terminates. The strong equality operator can be used to compare partial mu-recursive functions. This is defined for all partial functions f and g so that holds if and only if for any choice of arguments either both functions are defined and their values are equal or both functions are undefined. Equivalence with other models of computability. In the equivalence of models of computability, a parallel is drawn between Turing machines that do not terminate for certain inputs and an undefined result for that input in the corresponding partial recursive function. The unbounded search operator is not definable by the rules of primitive recursion, as those do not provide a mechanism for infinite loops. Normal form theorem. A normal form theorem due to Kleene says that for each k there are primitive recursive functions and such that for any mu-recursive function with k free variables there is an e such that the number e is called an index or Gödel number for the function f. A consequence of this result is that any mu-recursive function can be defined using a single instance of the mu operator applied to a primitive recursive function. Minsky observes pp. 94-95 that the U defined above is in essence the mu-recursive equivalent of the universal Turing machine. To construct U is to write down the definition of a general recursive function U that correctly interprets the number n and computes the appropriate function of x. To construct U directly would involve essentially the same amount of effort, and essentially the same ideas, as we have invested in constructing the universal Turing machine. p. 189. Symbolism. A number of different symbolisms are used in the literature. An advantage to using the symbolism is a derivation of a function by nesting of the operators one inside the other is easier to write in a compact form. In the following we will abbreviate the string of parameters x1, xn as x constant function. Clean users CQN equals Q, and Boulos Jeffrey use the abbreviation const TN equals N, e.g. C137 equals 13 e.g. const 13 equals 13 successor function. Clean uses X and S for successor. As successor is considered to be primitive, most texts use the apostrophe as follows. S equals a plus 1 equals defer, where 1 equals def0, 2 equals def0, etc. Identity function. Clean uses UIN to indicate the identity function over the variables she, BBJ use the identity function idin over the variables x1 to xn. UIN equals idin equals she e.g. U37 equals id37 equals T. Composition operator. Clean uses a boldface SNM. The superscript m refers to the mth of function fm, whereas the subscript n refers to the nth variable xn. If we are given h equals g, fm, h equals smn in a similar manner, but without the sub and superscripts bbj write h equals cn, g, f1, fm. Primitive recursion. Clean uses the symbol rn, where n indicates the number of variables bbj use pr. Given base step h equals f, and induction step h equals g, x. Example. Primitive recursion definition of a plus b. Base step f equals or equals u11. Induction step f equals g, a equals g equals c equals s. Our 2 U11 S PR U11 S. Example. Clean gives an example of how to perform the recursive derivation of f equals b plus a. He starts with three initial functions s equals a, u11 equals a, u23 equals c, g equals s equals c. Base step h equals u11. Induction step h equals g, a. He arrives at a plus b equals r2 u11 s13. Examples. Fibonacci number. McCarthy 91 function.